starting the weather briefing for today. Both me and Angelo, we work at the IPMA Institute, the Portuguese Institute for Seeing Atmosphere. We work here in this building, and we are somewhere here doing our presentation for this day. So, going for the first slide, the usual, where are you? You can use the annotations for identifying the country you're in. So both me and Angela are here. Portugal. And yes, we have some people near the Adriatic Sea, Central Europe. Yes. Pretty scattered. Okay, so moving for the presentation. So we have here the infrared image, 10.8 with the mean sea level pressure. You can see two lows, one in the North Sea, north from the British Isles, and another one near Italy in the Mediterranean. And also we have an eye here near over the Azores, and these are the three centers of action that are dominating the weather today here in Europe. So, looking up the higher level, we have the infrared 10.8 and the geopotential at 300 hectopascal. We can see we have also upper level lows associated with the lows at the surface. One at the North Sea and the other one at the Mediterranean. And we have here a trough, a small trough here over the Atlantic. So, as you can see, we have here the water vapor 6.2 superimposed with the isotex at 300 hectopascal, and you can see the jet stream going along here the Atlantic into the British Isles, and also here around the depression over the Mediterranean. Usually the dark colors are associated with the jet stream. We can also use looking for the Airmass RGB. We can see here let me point out just see the color, the intrusion of stratospheric air in this area, near the low over the North Sea, and also here we have some near the low on the Mediterranean. Let me just clear my annotations. And here you have a wave in this area of the Atlantic associated with the upper trough. This low over the Mediterranean has great strength. Is a quasi-stationary low, very active, and yesterday has already potentiated the flash flooding in Italy, and is moving very slowly into the Adriatic Sea, and it's the main focus today for European weather. But as you can see up ahead, we'll focus more on the low depression at the North Sea. As you can see here, we can use also the parameter of the height PV for identifying the intrusion of stratospheric air near the depressions. We are near the lows we are seeing here today. So, if you go to the Meteo Alarm link we have here, you can see the weather warnings for today in Europe, and they are mainly in the Mediterranean area. So let me just point out here, and you have here warnings for rain, thunderstorms, and wind. We even have a red warning for Croatia, and most of these countries in the Adriatic Sea have warnings associated with the depression. And then we have some warnings. I'm sorry, here in these areas, some warnings also for wind and significant wave height, and that's what will be the main focus for the next slides, associated with the low in the North Sea. So, start just a brief characteristic of the ASCAT scatterometer. And the scatterometer is used to derive the wind speed and direction over water. Here you can see at your right some main characteristics of the ASCAT. You can look at that with more detail later, but mainly is for deriving the wind speed and direction over water. You can go to the link of the OTISAF when you have a multi-platform product viewer, and it combines data from ASCAT from METOP A and METOP B, and it has the two products, the 25 kilometer resolution and the 12.5, which is the coastal link resolution, and for the last 22 hours, and you can click anywhere and get the data. We have some color-coded wind speed measurements, and we have the legend on the bottom. So if you click anywhere in the map here, we click near Portugal. We have the ASCAT passage superimposed on the infrared satellite image, in this case the Meteosat, and we have the winds, the direction and the intensity of the winds, and they are colored with according to the Beaufort scale. And then just to be more precise to the product, you can see the effect data acquisition here near the swath, and then we have the colored dots over some wings, and they give us the value of the maximum likelihood estimator, and this is very important for assessing the quality of the winds we are observing, and then when we are comparing it with the models we are using to forecast. So we will also use the altimeter to measure significant wave height. I have here this board just to show you, in case you don't know very well what is the significant wave height. So in this board you can see here is the increasing number of waves, and in the horizontal there is increasing wave height. So the significant wave height are the highest third of the waves, and it's the mean of that highest third of the waves. So when you are predicting a significant wave height of 3 meters, it can be a little higher and a little lower, but this is what it represents for you. We have here some on the left, some characteristics of the Jason-2. You can see also that later if you want with more detail. And the basic components for wave growth are wind speed, the fetch area, and the duration. So we need wind speed, the higher the speed, the higher the waves. The fetch is the area that the wind will affect, and the duration of the wind over that area. So looking at altimeter, we use this link here from NOAA, where you can get a various collection of altimeter data, and these are from 21 yesterday to 9 o'clock today, and we pinpoint this area here, so it's the main area of interest for us today. So when you click there, you get this zoom with the passage of Jason-2, Jason-3, Altimeter, GraphSat, and S3A through the area. And as you can see, yesterday around 10:31, we have here some significant wave height of 24 feet. So this is NOAA, so it's a US institution, so they use these metrics, unities. So, but I put here a table so you can see that 24 is around 7 meters significant wave height, which are well correlated with the prediction the models were outputting. So looking a little bit back, we'll use ASCAT to look at the fetch area, and as you can see here, we have winds that go up until this is the gale, and strong gale here at 43 knots. We have strong gale here, so this fetch area, as you can see here, it's 9 September, between 20 and 24 ETC, and as we go along in time periods, the fetch area is moving with the wind, and we have this area approximating to the Biscay Bay, where the waves will be higher than usual. So here I have put the ECMWF product for the mean sea level pressure with the wind speed, which is in colors, and the darker color here is the strong gale. Here, I'm sorry, let me just, you have some strong gale and gale. and this is valid for 6 UTC of 10th of September. And we also have the wind direction, the wind speed and the wind direction. You can see it here very well, but you can see it's in the northwest in this area mainly. So bear in mind the basic components of wave growth, which is wind speed, fetch, and duration. And so that started at 6 UTC 10th of this September, and now I will show you 6 hour step for the next for the prediction for the next hours. So this at 12 UTC, the fetch area is moving to the southeast with the winds increasing always, but here with strong gale, and then approaching the British Isles and the Bay of Biscay. The winds are not so strong, but they'll affect the wind of Biscay. So next we have here is the ECMWF product for significant wave height in colors. So the reddish colors are around 7-8 meters, and the mean wave direction, so the direction of the waves. And you can see here the strengthening of the significant wave height approaching the British Isles. You can see higher than 9 meters near the British Isles, and then affecting the Bay of Biscay, but with the winds not with less strength, so the significant wave height is also decreasing near the Bay of Biscay. But even so, there are warnings limited, so the significant wave height is it's important in this case. So just a little appointment for Hurricane Jose. We can see the Hurricane Irma because it has it's overland. So, but we search for ASCAT and Hurricane Jose, and here you can see it very well. And I'll show you. This is the passage of the ASCAT, and it's very well seen the circulation of the Jose that will be almost stationary around this area, and now it's a Category 2 hurricane. So now I'm passing to Angela.
Thank you, Bruno. Good afternoon. I hope everyone is listening clear. I'm going to change completely the subject. I'm going today to talk about upper level lows and the conceptual model. So these lows have typically they have a close circulation in the middle and upper troposphere, and they are relatively long-lived lows. The life cycle consists of 4 stages: upper level trough. Just a minute. So upper level trough. This one here, the tear-off stage, the cut-off stage, and then the final stage. This evolution, this life cycle consists of the upper trough is detached from the mainstream until it finally fills up or merges with another trough. I'm going to show you in the next slides an example of an upper level low that developed some days ago over North Atlantic near Azores. In this red box on the right, you can see model parameters, which are the key parameters of this conceptual model. So the first image is from 4th of September at 12 UTC. This is the upper level trough stage, and I'm using here the 300 hectopascal height because it was easier to show you the patterns. The area we are interested in is the left side of the image. So this one here, over this area over here. So you can see the upper trough in this area behind the frontal zone that is ahead of the trough. And this trough has a backward oriented inclination with height. You can see it over here. And also we have the cold advection within the trough. You have here, you can see with temperature. The temperature is the blue, the dark blue. And we have the warm advection in the ridge, so in this frontal area. 24 hours later, on the 5th, 12 UTC, the upper trough was already in the second stage, where when this stage means the bottom of the trough is detached from the mainstream. In this image, I think we are at the end of the tear-off stage, because the cold core is already detached from the mainstream, as you can see with this closed blue line in the center. You can see over here with this closed blue line in the center. So the cold air, I told earlier, so the cold air flows into the middle of this this kind of inverse omega shape that you have here. So 2 days later, on the 7th of September, so last week, the upper level low was in the third stage, so this is the cutoff stage. And in this stage, one of the things that can happen over a warm surface is convection. This is, of course, this is a warm surface because we are in the late summer, and the sea surface temperature is relatively high in this latitude. So we can have convection, it can happen within the core of the upper level low, but also ahead of the low in this area of a thickness ridge. I'm not showing you the thickness parameter, but is over this area over here. So moving on, this next image is from the, we have here the 1000 hectopascal height on the same day, and you can see at surface a weak circulation, a weak circulation may appear in this upper level lows conceptual model, but this is not the case. We have here a high pressure system over Atlantic, over Azores, and it was difficult to find even a weak circulation, a cyclonic weak circulation at 12 UTC on the 7th September. So, one question for you. Another key parameter of this conceptual model is potential vorticity, and in the area we are interested in, of course, do you think there is a potential vorticity anomaly near the upper level low? If yes, can you show with the annotations tool, please? Okay. Okay, I see some information. Okay. Well done. Yes. Yes. Perfect. Yes. Yes. I must say that I'm not sure. Of course, in other areas, I was thinking about this low system south of Azores, but of course there are another areas with potential vorticity anomaly. Very well. Okay, just moving on. I'm not sure if this over Iberia is a PV anomaly. I'm not quite sure. Maybe it is. I don't think so. But well, I don't know. Maybe we can talk, if we have time, we can talk it later. Okay, just to move on, just to remember, of course, you already know why we have here a potential vorticity anomaly, but just to remember, so this is the Airmass RGB receipt, and we have here the reddish color. Why we have the reddish color? So this is dry, cold air from stratosphere, and the first brightness temperature difference is very smaller, so we are talking about the water vapor, and we have a large contribution of red. In the middle, we have the green beam, so we have the stratospheric air that is ozone rich. If you remember, we have here the 9.7 infrared, and this brightness temperature difference is strongly negative. So we have a low contribution of green, and the contribution of blue is very small. So we are talking about the water vapor. So it's very small. So the final color will be this reddish color over this area. So this is a potential vorticity anomaly, and usually can indicate it can in the next hours we could have some convection over here, and in fact we have at this on the 7th, 2 days later, we have this convective cloudiness south of Azores. So we have to see that sometimes these upper level lows produce convection, and sometimes it's severe convection. So moving on, I want to show you how the upper level low looks like at the water vapor image. The most cases, upper level low, the appearance at the water vapor image is a spiral of gray color. So this is Iberia over here. So this is the low, upper level low we are talking about in this area over here. And so the conceptual models say that we have in the water vapor image a spiral of gray color. And it's not very well seen in this case, but we can imagine that there is, we can see some convection, cyclonic circulation over here, so there is a spiral. In the perfect cases, we have in the middle a more dark area because of the dry air in the core of the upper level low. So we can see the spiral better. So we were talking about this upper level low, and it was in the middle of the North Atlantic. You remember, south of Azores, more or less. So do you think this can be a threat to marine users? So I mean, you saw the surface field and there was a high pressure system. These lows occur in the middle and upper levels. Okay, we already have some answers, and they say yes. Okay, very well. You are very good forecasters. Very well, very well. Yeah, I think everyone agrees. It can be, it can be also no threat scores, but in this case, particularly in this case, I think it can be a threat. Okay, let's move on. Okay, it's a threat. We all agree. But tell me, why is it a threat? Can you tell me some of the weather phenomena or threats that I put here? There are lots of, maybe some more. Okay. Oh yes, you're perfect. That's very good. Yes, yes. Of course, we are talking about convection. So perfect. Of course. Okay. I'm not sure about big waves. In some conditions, big waves may be a threat. Mostly in the winter time, not necessarily related to the upper level low, but related to the swell. So the Atlantic in the winter is very busy, and sometimes when we have these upper level lows with swell, it can be a threat. But in this case, in particular, the big waves were not the main threat. Okay, just to end, this is from SatManu, so you can check it later with more information. So these are some weather events over sea. You can see also in the SatManu the weather events over land. But these are the weather events over sea, and you can see some the moderate to heavy showers. Also in the winter season, some snow, thunderstorms, hail. Thunderstorms they are a threat also because of lightning. Lightning can be a problem with the communication system of the boats, the vessels, and of course with convection, strong gusts around CBs, of course, it's very important. Not for marine users, but for aviation, do not forget the risk of moderate to severe icing and turbulence. So you can see here that upper level low has a lot of weather events associated. And just my last slide to show you, going back to ASCAT that Bruno mentioned, it's for us, it's a very important sensor because we have lots of sea to monitor, and you can see this image over here with the Airmass RGB and the convection southwest of Azores. Azores are these black dots over here, and you can see this in the middle of these green bars. The green bars are 20 knots, more or less. In the middle of these green bars, you can see some higher values of wind speed, around 25 and 30 knots. So these winds can be related to convective gusts. So this, do not forget that ASCAT, it's surface wind retrieval. So this is happen at the surface. So it will be a threat for a vessel or a boat that is in the area. And thank you very much for your attention. And I don't know if you have any questions.